Okay, now remember that we are talking about the axiomatic approach to probability theory. And in the axiomatic approach, what one does is you list a hopefully small set of axioms. In this case, a set of axioms that we think a probability function ought to satisfy. And then we develop the theory from these axioms. All right, and so that is what the axiomatic approach to probability theory does. It lists a very small number of axioms. And in this case, in this course, we're going to use these three axioms. All right, and from this three set of axioms, we are going to develop all of the theory that we need. Now, let me just say that in a more advanced course on probability, you would look at a different set of axioms. All right, a set of axioms, some of which are at a higher mathematical level, and therefore allow you to do more higher level mathematics. And let me also say that the study of probability can be approached at a variety of levels. It's kind of like peeling an onion. You can start off studying probability at a very basic level. You peel that outer layer off. And then you're prepared to study probability theory at a little bit higher level. So that's the next layer of the onion. And really, you can study probability at whatever, at high a level, mathematical level as you can possibly imagine. I mean, you could get a Ph.D. in mathematics studying probability theory. All right, there's that much to it. So there are different levels at which one can study probability theory. The level that you have studied probability theory in courses, most previous courses in college, and certainly courses in high school and so forth, those would be at really the lowest level that one could approach probability theory. This is one or two steps above that, this axiomatic approach. Okay, and but just keep in mind that if you are interested in this, you can continue your studies in probability and look at study it at even higher and higher levels. Okay, so let's look at these. Let's look at this setup. Let's look at these axioms and see what we can come up with and derive from these axioms. So let's consider a random experiment that has a sample space which we'll denote by uppercase or capital S. And suppose that there exists a function. Okay, and we're going to denote that function capital P, and this function satisfies the following three axioms. Okay, axiom 1, A1, is that for every event associated with the experiment, all right, so every event that is a subset of the sample space, then I said probability, we're not calling it that yet. This function P evaluated on that event is at least 0. And so let's think about this for a minute. P is a function, the argument that takes arguments that are events. In other words, this function takes sets as events. And then this function returns a real number. And what we're saying here is that real number is always going to be non-negative. It's always going to be greater than or equal to 0. Axiom 2 says that if we evaluate this function P on the sample space of the experiment, then the real number that it evaluates to is 1. And then axiom 3 says that if the two events A and B are mutually exclusive, then the probability that at least one of the two events occurs is equal to the sum of the individual probabilities. In other words, the probability, I keep saying probability. Let me say it again, this function evaluated on the event that at least one of the two events occurs is equal to the sum of the values of the function evaluated at the component events. So the function evaluated at A and this function evaluated at B. And so what follows then, if this function P satisfies all three of these axioms, then we call P a probability set function. Okay? And this function evaluated at an event A, is called the probability of the event A. So you can see here that from a mathematical standpoint, we are defining probability at quite a bit of a higher level of abstraction than we do when we talk about simple situations where we're tossing coins, flipping, rolling dice, and things like that in a much more elementary course. All right, so we're approaching this from a higher mathematical level, and so we're going to be able to do things like derive properties and so forth, utilizing that higher level. Okay, so what kind of properties does a probability set function have? Well, I've got 5 properties listed here, and there are more as well that we'll see as we go on. But these are some of the more basic properties that we can derive and prove based on the axioms on the previous slide. And let me just point out here that in setting up our definition of a probability set function, we have not talked at all about what type of probability we're talking about, whether it's a classical probability, a relative frequency probability, or a subjective probability. The only 3 things that have to be true in order for a function, and in particular a set function, to be a probability set function, is that these 3 axioms have to be satisfied all the time. Okay? And it's from these 3 axioms that we can derive these properties. So the first property, property 1, that we can derive from the 3 axioms is that the probability of the null event, we'll call this the null event, is 0. All right, so the probability associated with an event that contains no elementary events is 0. And if you think about it, that makes eminent sense. All right, but the question would be, even though it seems obvious, how would you prove that? Now the second property, property 2, is that the probability of A is equal to 1 minus the probability of A complement. In other words, the probability that A occurs is equal to 1 minus the probability that A does not occur. Now we could rewrite this and we could solve this equation for the probability of A complement, and we would have it expressed as we expressed it before in the context of, I believe, relative frequency probability. And expressed that way, we would say that the probability of A complement is equal to 1 minus the probability of A. So the probability that A does not occur is equal to 1 minus the probability that A does occur. And again, that is called the complement rule, and it's a very, very important rule. We may use the complement rule more than any other rule or any other property that we come up with. Property 3 says that if the event A implies event B, then the probability of A has to be less than or equal to the probability of B. Now, if you'll think back to our discussion of relative frequency probability, we also had this property, okay? And so we're seeing here that using this more general abstract approach, we can obtain the same kinds of properties that we got when we were focusing on the relative frequency approach to probability. Property 4 says that the probability that at least one of the 2 events A or B occurs is always going to be equal to the probability of A plus the probability of B minus the probability that both A and B occur. Now, this is called the general addition rule, and again, this is always true. All right? And then finally, property 5, which is called the Bonferroni inequality. This property says that the probability that at least one of the two events A or B occurs will always be less than or equal to the probability of A plus the probability of B. Now again, properties 4 and 5 were properties that we listed as being properties of relative frequency probabilities. So again, using this more general approach, this more abstract approach, we're coming up with the same kinds of probabilities that we saw when we were talking specifically about relative frequency probability. And that makes sense. That ought to be the case, shouldn't it? All right, because what did we do when we first started out listing these axioms? We said we wanted to list axioms that made sense, and that we thought that any kind of a probability set function should satisfy. All right, and if you look at these three axioms, we know, we know at least two of these, because A1 and A3 were actually properties of a relative frequency probability. Now, we did not show this one, and we did not list that or prove that as being true for relative frequency probabilities, but it is true. Okay, but it shouldn't be a surprise then that if these axioms make sense for a probability set function, then we should be able to come up with properties, or the properties we come up with should be those same kinds of properties that we would get if we focused specifically on relative frequency probability or on classical probability. Okay, now let's think about how to prove some of these results. I'm not going to prove them all here. I'm going to prove some to give you an idea of how we go about proving these, but I'm going to save some of these for you to do. All right, so the first proof we're going to look at is the proof of property 1, which says that the probability of the null event is equal to 0. Now again, this seems completely obvious, almost too obvious to prove, but we do have to prove it. And the way that we have to prove it in this more general context is to utilize the axioms. Because we're looking at this in this more general context and we're not specifying a particular type of probability, we cannot use an approach that is specifically tied to a particular type of probability in proving these results. For example, we can't use an approach used for relative frequency probabilities to prove these properties, because this is more general. It's a more general framework than that. So let's see how we can prove this result. So the first thing we're going to do is represent these events in slightly different in different ways. So note that if we this is an event right here. It's the event that when performing an experiment, either an event in the sample space occurs or an event in the null set occurs. We can think of this as the union of two sets. Okay, and when perhaps it's easier to think about it in that context. The union of a set with the empty set is just that set there, right? We're not combining anything with that set because this set is the empty set. And so S union with the empty set is just S. And then if we think about the set of elements, the set of elementary outcomes that are common to both the sample space and the empty set, well, because the empty set does not contain any elementary events, the intersection there has to be the empty set. Okay, so we've got these two relationships. S is equal to S union empty set, and the empty set is equal to S intersect the empty set. Okay, so we use these two results below. So note first that we can rewrite the probability of S, the probability of the sample space, as being equal to the probability of the sample space union with the empty set, because S is equal to S union empty set. Okay, and notice also that because the intersection of the sample space with the empty set is the empty set, what does that tell us? That tells us that the sample space and the empty set are mutually exclusive, right? Remember that definition? If the intersection of two events is the empty set, then those two events are mutually exclusive. Now let me go back 2 slides to the page of axioms. This axiom 3 said that if two events A and B are mutually exclusive, then the probability that at least one of them occurs is equal to the sum of the individual probabilities. So we're going to invoke axiom 3, all right, in this statement here, and going from this step to this step. And so now we have the equation, the probability of S is equal to the probability of S plus the probability of the empty set. Well, now I can subtract the probability of S from both sides, and what that leaves is 0 being equal to the probability of the empty set. And so that is the exact result that we were wanting to show. So that ends the proof. That's how we do this, and you see that all we did was use some of the axioms, and in particular, we used axiom 3. We also used the fact that if the intersection of two sets or two events is the empty set, then those two events are mutually exclusive. All right, now let's prove the complement rule. All right, and in this form of the complement rule, the probability of A is equal to 1 minus the probability of the complement of A. So again, we're going to note some useful results. First, that the union of the event, well, let's think about this as a set first. So the union of the set or event A with the complement of A is going to be equal to the sample space. All right, so what this says here, we can think about this. The outcome of the experiment is either an A or it's not an A. All right, and so the union of those two events is the sample space. On the other hand, the intersection of those two events is the empty set, right? Because the set of events that are in A are not in A complement, and likewise, the set of elementary events that are in A complement are not in A by definition of A complement. And so what this means is that A and A complement are mutually exclusive. All right? And so let's put this together and make an argument out of this. And so we know by axiom A2, in fact, let me go back to my set of axioms here. Axiom 2 says that the probability of the sample space is 1. Okay, and so I'm invoking axiom 2 right here. But now I can rewrite the event S, the sample space, as A union A complement. So I put that in there, right there. Okay, and then because A and A complement are mutually exclusive, I can again utilize or appeal to axiom 3 and rewrite this complicated probability as the sum of individual probabilities. And so here I have the result that the probability of A plus the probability of A complement is equal to 1. And if I want, I can subtract the probability of A complement from both sides to get the representation I've got up here. And so that would lead me to the conclusion that the probability of A is equal to 1 minus the probability of A complement. Okay, so we have our result. And again, we haven't used, well, all we've used here are axioms. All right? And we haven't used any other properties. Now let me just say that we do have 5 properties. Let me go back here. We've got 5 properties that at some point we're going to be able to make use of in proving other properties. In proving these properties themselves, we can only use axioms or properties that we previously proved. So we proved property 1 using only axioms. Now once we've done that, in proving these other properties, we could use axioms or we could use property 1, or property 1. Since we've already proven property 1, we can use it. Now likewise, we proved property 2, and in that case we did not need property 1. All we needed were some axioms. And so, we're at the stage now where we've proven properties 1 and 2. Now in proving properties 3, 4, and 5, we can utilize the axioms, and we can also use properties 1 and 2. Once you've proven property 3, then in proving properties 4 and 5, you could use the axioms as well as properties 1, 2, and 3. So you see how the game is played, the mathematical game is played. Okay, we cannot use a property until we've proven it, but once we've proven it, we can use it whenever we want.